Giant. Giant is a dream that many of us had about now almost 15 years ago in realizing how important is to be excellent, specialized, but at the same time working together. This is the concept of ecosystem, where every element is important in order to have an harmonic development. And in our case, the development is to be useful to the citizen, to be useful to society, to learn from fundamental science, then to put this knowledge at the service of innovation, and from that, give opportunity to industry, and at the end of the line, create jobs for the citizens. And there's a key element that joins all these elements. And this key element is the education part. The role of the young generation, the role of fuel of this process that requires dedicated, excellent minds. So working together, we are trying to do that. And we are doing it by, as you can see here in the giant map, by connecting different activities where excellent institutes are all operating in. So if we look from the left, we have what we call the EPN campus, the European Photon and Neutron campus, where we have the brightest X-ray and the neutron sources in the world. And we have also a European laboratory for structural biology, the EMBL, as well as a French laboratory, the IBS, financed by the CA, CNRS, and UGA, who does structural biology in connection with the use of X-rays and neutrons. Then we have an area of fundamental research that sees the engagement of CA and CNRS, as well as with the contribution of the University Grenoble-Alpes. Then we have an area which is fully dedicated to apply research to energy. What do I mean energy? For example, there's a lot of work going on energy storage, on hydrogen science for future applications. And then there is the part dedicated to information and communication, which is very, very important. And this is essentially the CA, but in connection with other industrial partners, in particular ST Microelectronics, as well as many startups. Then we have an area which is dedicated to healthcare. What does it mean? Healthcare means bringing innovations to the service of health procedures. So all this then has to be shaped and put together into an urban settlement. So there's been also investment in order to create a residential area and conglomerate all these activities into a sustainable citizens' life with the presence of families, of residents, of students, of professors, of visitor, long-term and short-term, and so on and so forth. So this is what we have today, and I will tell you that there's been a lot of work going on over the last 15 years, and we will see something about that. And these are the founding members, and as you can see, higher education, fundamental research, technological research, European research infrastructures, and technology management. After that, we have increased our connections with partners, both industry and investors. And I want to underline also many, many startups, small startups, beside the giant industry that you can see here. And all that has also heavily benefited from the involvement of the local and regional and national authorities who have been able, through various programs, to contribute to the giant development, as well as to the urbanization of the giant area, so that it's not just lab, it's also a way of life. If we look a little bit into the numbers, again, is a different way of looking at what I just said before. We have two French regional research centers, 8 major French European research labs and infrastructures. We have today something like 23,500 researchers, counting public and private, within a radius of about 20 kilometers. So this is also takes into account other areas in the Grenoble area. We have a total of 63,000 students in Grenoble, of which about 40% in scientific fields. And Grenoble has been a very attractive city for France. In fact, it was the #1 in 2017. And according to the Forbes magazine in 2013, was rated as the 5th most inventive city. And I also want to underline that since 2000, there have been almost 500 startups, actually more than 500 startups that were created. A little bit of history. You know, everything started in 1956 with the installation of the CENG of the CEA, the Center for Atomic Energy, and the CNRS, the Center for National Research in France, followed right after in 1962. In 1967, France and Germany at the beginning decided to build the European high flux reactor. This is a reactor which produces a neutron for research, thermal neutrons. So this is the big tank that you see here, in which the reactor is contained. In 1988, we came, Esrf. In fact, I was at the labs and I came here in 1991 as a scientist to build one part of the Esrf. And then Minatech was created in 2005 from micro and nanotechnologies and is one of the pulsing heart of the giant campus. And in 2008, we founded Giant, an alliance for innovation in the world. And I want also to underline that 2020 is an important year for us at the Esrf, because as you will see, we just started to operate a new storage ring, a new X-ray source that makes us very special in this moment. So, if we look at how the situation has evolved over the last 10 years, about 1.8 billion of euros have been invested in the area. And starting in 2008 with something like 5,000 students, 6,000 researchers, 5,000 industry jobs, and 300 inhabitants, what we are reaching in 2021 is the goal of the 10,000, 10,000, 10,000, 10,000. So the objective, as I have tried to explain, but you will see it better in this view graph and in all the material that we will receive, is again to try to bring all this know-how, all this centers of excellence to work together on specific team. And the team that are at the heart of the Giant action are, as I said, in the area of information, energy, and health, and indeed responding to some of the key societal challenges that we have today in order to ensure in the long term a sustainable life on our planet. And by removing barriers to create further science of excellence, which are the so-called thematic districts, we are able, we hope, to continue to improve in the coming years this dream that sees everybody with their own expertise working together. And you can see here all a series of activities and buildings. I will not go through all of them, which host 10,000 researchers and 10,000 students, which were created during the last decade. And many of them are still in construction, like the Innovation Center that you may see on the Mandela Place. Also, you can see here all the aspects linked to urbanization of the giant campus, which requires residents, but also require transport and connection with the rest of the town and the rest of the world. And we are, of course, very sensitive to all the environmental issues. And we are trying to connect the giant campus inside the campus and towards the outside as green as possible, minimizing the carbon footprint with the use of the tram, the use of electric shuttles, so the use of bikes, the use also of a telepheric that will be created soon in order to connect the different tram lines. Beside that, there's been a major economic transformation with the creation of about 10,000 industry jobs. And in that sense, ST Microelectronics and Schneider Electric are really key to this process. But also want to mention a startup that built up into a major company for innovative instrumentation in X-ray and neutron science, Xenox, as well as the headquarters of the Crédit Agricole that decided also to install themselves on the campus next to the Oxford Bridge. So this is just to give you a feeling of what the giant is. Now let's go into that part of the campus that we refer to as the EPN Science Campus, where, as I said, we have 4 institutes, the Esrf, the ELL, the EMBL, and IBS. Again, here, the main theme is science. So we have something like 500 scientists on campus and about almost 2,000 people altogether, including engineers, technicians, and administrators. 3 organizations are European, meaning they have a governance which is established through an intergovernmental convention or a treaty. And 1 is French, the IBS, which is a collaboration, as I mentioned, between CA, CNRS, and UGA. We have a lot of partnerships within the campus, like the PSB, the Partnership for Structural Biology, the PSCM, a partnership on the study of condensed matter. We have created together, all 4 partners, a cryo-EM platform. This is the state-of-the-art cryo-EM that allows today to look at biological material with atomic resolution. There are few of them around the world, few of them in France, and the one on our campus is operational since 2017 and is the first and so far the only one who's open to whoever wants to use it on the basis of a proposal that is judged by the panel and accepted on the basis of its scientific excellence. All the other cryo-EM around the world and in France are basically inside labs and are part of the lab activity. So they are not open platform that can be used also by a small university or a small research center that will never be able to afford such a complex apparatus. So let me now turn my attention to the ESRF, this big donut that is also the eye of the Dove of Peace, that is one of the symbols of the Grenoble area, and indeed this part, the top part of the head of the dove, is the giant campus. So ESRF, what's the ESRF? ESRF is an intergovernmental agreement among 22 countries that get together, put their best people, and finance an activity that none of these countries would be able to carry out by itself. And this allowed in 1992, when I came, to have the first, what we call a 3rd generation synchronous source. Perhaps we will explain later on what that means. But this was something extremely innovative that, as compared to previous use of synchronous radiation, improved performance by a factor of 100 to a factor of 1,000. And we were the first, and it was a huge innovation that then spread all over the world. And today we count something like 30 of such sources. And today, in August, end of August of 2020, we have started a new adventure by putting into operation, after a 1.5 year of shutdown, a new accelerator that we call EBS, for Extremely Brilliant Source, which is a completely new generation of high-energy synchrotron sources as compared to the third-generation sources. And I will tell you a little bit later on about this. Just to give you a feeling, as I mentioned, we are funded by 22 countries. Every year, we welcome something like 10,000 scientists. We have 44 instruments that are put at the service of these 10,000 scientists on the basis of scientific excellence. We were key for the achievement of 4 Nobel Prizes. We have every year something like 2,000 publications coming from the work of the scientists from all over the world coming to Esrf. And we are just completing a 330 million investment program to create this new EBS source. So what do we do exactly at the Esrf? You know, what the key point is something that I think has been always one of the characteristics of humankind. The curiosity to understand the nature and the world that is surrounding us. And in particular, understanding the materials and the living matter that is around us has been always one of the key drivers for human progress. I just remind you that many era of human activities are identified with a material, the Stone Age, the Bronze Age, the Iron Age, the Steel Age, the Silicon Age, the Oil Age, and so on. And what is the process? The process is that we want to understand the function of materials and why certain materials behave in a certain way, and link that to the structure that form that material, and eventually all the way to the atomic structure. When we can understand the relation between function and structure, then we can try to make new materials, trying to improve performance. And we can study, we can imagine to create these materials, and then we have to do the processing to create these materials. And once we do the processing, we change the structure, we change the function. And all these aspects are linked to each other, but there is a key element that joins them all, that is the characterization of the material, the analysis of the material, understanding the structure and relate that to the performance, the properties, and the processing. And this is where synchrotron and, in general, accelerator-based photon sources become a key issue. Synchron-like sources allowed, in this sense, to address critical global challenges in areas such as health, environment, energy, food security, and in particular, in condensed and living matter, synchronous science link functions and properties to the structure of the atoms. And so what we do is X-ray science. And, you know, since their discovery in 1895, X-rays have been key for a spectacular success in science in general. We can say that the last century was really the era of crystals. We were looking at ordered materials using X-rays to understand the structure and link it to the properties. But today we're entering into a new era, which I define the era of complexity, where we really want to understand from the atoms all the way to the macroscopic object, all the different hierarchies that organize matter and define the certain functions that then are critical for their use or understanding the way they can be applied to everyday's life. And this explains, as I mentioned before, why we have so many synchrotron sources around the world. We have something like 30, as I mentioned, they're all third generations, and they serve something like 50,000 users at the world level, and the Esrf about 10,000. So almost 1/5 of the people comes at the Esrf at least once a year, but they also use other facilities, of course. And and it's clear since some years now that there was real need for the next step. And what is the next step? As I said, in order to understand complexity, you cannot rely anymore on the long-range order of crystals, but you need to be able to look from the single atom all the way to the macroscopic object. Just take as an example a life science, where you want to understand the structure of protein and then how these proteins organize themselves, for example, at the subcellular level, then the cells, then how the cells joins together to make tissues, how the tissue joins together to make organs, how the organs work, all the way to the human body. And to be able to do this zooming in a continuous way, penetrating and not destroying the material by sectioning and looking at piece by piece and put things back together, is really what is the aim of X-ray science in the coming years. And why X-rays? Why not lights? Why not some other kind of particles? What's special about X-rays? Discovered by Röntgen in 1895 and first Nobel Prize. Yeah, I forgot to say that X-ray science, was written here, produced something like 25 Nobel Prizes altogether, and the first Nobel Prize was given for the discovery of X-rays. So what's so special of X-rays? Nothing particularly special. It's light, but the wavelength of this light is very much comparable to the typical distance between atoms. So X-rays is light that can resonate, can diffract from couples, pairs, or assembly of atoms that are one next to each other. So it's a light that allows us to see atoms in a very, very direct way. And what's special about synchron radiation? Well, since the Röntgen time, the way to produce X-rays was to accelerate electrons on a cathode, and bombarding the cathode with this electron, you produce X-rays. So this is what is called the rotating anode, because you keep this cathode turning so that it doesn't heat up. And these rotating anodes haven't changed much from the beginning of last centuries until now. And this is what you find in a hospital or in a typical lab. But there is another way that's known since a long time to produce light, is to take a relativistic electron and put them into a magnetic field. Because if you change the trajectory of a relativistic electron, the electron loses energy by producing light. And this is exactly what we do here. Now there is a little animation, I don't know if we can make it. So you have an electron, you put it into a magnetic field, and this electron produces light. And you can see it in this next slide. So the fact of applying this dipole that changes the trajectory of a relativistic electron emits light. So the electrons loses a little bit of energy that is produced in light. And at this point, you can understand the basic functioning of a synchrotron source. This is also a video in which you have, like a Esrf, a 1 kilometer accelerator where you rotate relativistic electrons, and because they change the trajectory, they produce light, which is sent in all a series of what we call beamlines, where you do your experiment with very sophisticated means. You see here, for example, an experiment of a nanocrystal of a protein. This is a big detector. So this is just in 2 words, what's synchron radiation. Why synchrotron? Well, it's very simple. If the electron emits light and you want to keep it rotating, you have to give back the energy that the electron have lost in light. And you do it with a radio frequency that in a synchronous way gives back a kick to the electrons that have lost synchrotron light to be again ready to give light at their next turn in the storage ring. So, so you can see here in this view graph the difference between what you can do with the rotating anodes and what has been done with synchron radiation. You see this huge increase of source quality, what we call brightness or brilliance, which today is about 100 billions more than what you can get in a laboratory. source. And this comes the Esrf, the decision of creating such a facility from these different countries. And these are our core missions: the design, construct, and operate and develop a state-of-the-art X-ray synchrotron instrument to the benefit of the scientific community of the member and associate countries, as well as of every scientist in the world. And in that respect, over the last few years, we have conceived at the Esrf a revolutionary design of a new storage ring that allows to boost performances by something like 2 orders of magnitudes. This was a big project that started in 2015. The decision by our council was taken in 2014. 2015 marked the beginning of the construction process that was carried out while the other storage ring was still operational until the end of 2018. In 2018, at the end of 2018, we had all the new source ready to be put into the 1 kilometer tunnel. This is something like 1,000 magnet, 129 girders. You know, it's a huge operation. And we were able in 2019 and 2020 to empty the tunnel, put the new ring, commission it, despite the major sanitary crisis that hits us all since last year, since March last year. We were able to reach the goal of putting the new source in operation as planned on the 25th of August. And so today we have this new source operational. And what is quite rewarding is to see what's going on in the world. There is about already something like 15, 16 projects to do upgrades of existing sources in the US, in Japan, as well as in Europe, exactly in the same direction and using the same principles of the Esrf EBS. So this explains you also one of the characteristics of the Esrf and one of the characteristics of Giant, that by bringing forces together, by bringing excellence together, you show the way for the next big steps in all fields of science and innovation. So coming back to our mission, the second point is to serve the international community for the advancement of knowledge and to address global societal challenges. And this gives you just a very quick view of what we do, and you can see the tremendous number of applications that goes from biology and health, energy and environment, new materials, space and transport. We also do a lot of cultural heritage, because with X-rays you can penetrate without destroying, so we can see for example, fossils and work in paleontology in a way that has never done before. We also, due to the brightness of the source and the fact that we can put so many X-rays in a very small volume, we have a lot of application at extreme conditions to understand the new materials. So, for example, for the ITER project, as well as understanding planetary conditions. So we are doing a lot of work today in trying to understand the extreme condition existing in planet Earth, and at the same time applying the chemistry at extreme conditions as a study of possible evolution of planets, existence of exoplanets, and so on. Another area of application is, of course, in micro and nanoelectronics, chemistry and catalysis, and a lot of work is also going on food supplies and environment pollution. To be noted that this is not only fundamental science. About 30% of the work carried out at the Esrf is done in collaboration with industrial partners. So if I have to summarize the very wide science case that is behind the construction and the operation of such a large laboratory, we have done an exercise very recently, last year, in view of the new framework program 9 called Horizon Europe that the European Commission is launching, and also in full consistency with the Sustainable Development Goals that have been published last year by UNESCO. And you can see it here, the 7 themes on which we are highly concentrated: health innovation, overcoming disease and pandemics; 2, materials for tomorrow, and innovation and sustainable industry; point 3, clean energy transition, sustainable energy storage and clean hydrogen technologies; planetary research, terrestrial and extraterrestrial, exactly in the sense that I told you before, that we can create in the lab extreme conditions that then we can study with X-rays; environmental and climatic challenges, bio-based economy and food security; and finally also humanity and world cultural heritage. And now it will be my pleasure to conclude with a few viewers by giving you some examples of this science. And I just want to start with this one because I think is the most touchy one, and is something that despite all the difficulties and the fact that we were in the middle of the commissioning of our new source when the COVID-19 virus broke out last March, we gave immediately priority in the commissioning process to all our instruments that could contribute to the understanding and to the actions that could contribute to overcome the pandemics. And we put the 4 beamlines and the cryo-electron microscope platform immediately on COVID-19 research since June of last year. And we did it again in strong partnership with the EMBL, the ELL, and the IBS. So basically, other 2 international centers, plus the CNRS, the CA, and the UGA. Again, with a very strong imprimatur, with a very strong and clear role of giant. But also, we started something that is completely new, and is bioimaging. We have created this new source that is so bright and so powerful in some sense, that allows to do and to penetrate into object in a way that has never been possible before. And therefore, one of the key questions that we were asked whether it was possible to be addressed with a synchrotron is, can we look into a COVID-19 affected lung? Can we understand how a lung is being destroyed by the virus? And so in collaboration with hospitals, in particular from Germany, and UCL, University College in London, where there is a team of people that is world leading in medical imaging. We took a COVID-19 lung and we scanned it for the first time with this new EBS source. And now I have a video that we can start. And and I think there is also the audio.
The recent EBS upgrade to the European synchrotron in Grenoble has created the world's first high-energy 4th-generation synchrotron, which is currently the brightest X-ray source in the world. With this upgrade, scientists are now able to see inside whole, intact human organs with an unprecedented resolution approaching 1 micron, which is approximately 1/50th of the width of a human hair. This volume reconstruction shows the fixed right upper lobe of a 54-year-old male COVID-19 victim who passed away after prolonged mechanical ventilation from pulmonary and multi-organ failure. Inspection of the large conducting airways shows plugging of subsegmental bronchi, as well as pattern-occluded blood vessels, here in red and yellow respectively. Zooming into the peripheral respiratory zone of the lung, architectural distortions of the gas-exchanging pulmonary alveoli become evident. Here, depicting 2 neighboring structo-functional subunits of the lung, with preservation of the fine cup-shaped pulmonary alveoli in one lobule and plumb-dilated alveolar ducts due to alveolar collapse in the other. There is growing evidence that alterations to the vascular system play an important role in the pathophysiology of COVID-19 pneumonia. The hierarchical, scale-spanning nature of our method allows for the visualization and three-dimensional assessment of complex vascular systems of the lung, down to the smallest capillaries that are involved in alveolar gas exchange. All this can be done non-destructively from virtually anywhere within an intact organ.
So I think we can stop here. And this movie was done in the frame of the announcement of the Chan Zuckerberg Foundation that gave to the Esrf and UCL at the beginning of December a €1 million contribution to this research. And today this is even growing because the experiments that are going on as we speak are on many other organs, in particular the brain and the kidneys. But in general, what you have seen here is something that humankind has never seen before. This precision and the quality of this imaging are basically astounding. Today, all this kind of work was always done by histology, by basically taking a certain volume and cutting it in pieces and looking with microscopes. And it was a very lengthy and also destructive work. And for the first time, humankind can look inside these organs with a precision which is as high as we wish. And it's clear that the applications are enormous, numerous, both to understand how a disease spreads over a body, but also to simply understand the body and its aging and many other processes that until now were really impossible. And it's with proud and also with some emotion that, you know, I would have to have a man which is called Leonardo Da Vinci, and he is recognized to be the first person in humankind to take a truly analytical and scientific approach to understand human organs by, first of all, describing them, and then try to understand each part of this organ, what function has in the life of a living body. And we see these drawings that were made by Leonardo about 500 years ago in Milano, and now we see this incredible EBS imaging that is done in Grenoble 2020. We can almost say the anatomy of the 45th parallel. So this is, I think, gives you a little bit the feeling of the huge excitement that we are living these days. Let me give you also other more light examples of science that is being carried out during these days, like, for example, application in cultural heritage. The work with a synchrotron allows, by looking at very small chips, to study unique objects, like, for example, in this case, the Scream of Munch. And the aim of this study was to understand the role of moisture in the degradation of the colors. This just to give you an example. Or when we talk about environmental studies, this is a work that has been done to understand the dark earth that you find in the Amazonian forest. This earth is being studied because it's much more effective and much more efficient in favoring the life of vegetations. And the researchers want to understand all the chemistry and all the processes that from the microscopic atomic level, the role of organic carbon and phosphorus then favors the growth of vegetation, and therefore try to use these principles in order to make other soils as efficient, and maybe to use it to trap CO2 and so on. And let me just switch to the other point, which is the support and the use of X-rays by industry from member and associate countries to strengthen the competitiveness on a global scale. Again, one important role of Esrf is to favor proprietary research when X-rays are required to understand advanced process in industry and in innovative projects. In this case, industrials, of course, pay the service at a real cost because Esrf is organized as a no-profit organization. And we have instituted a very innovative collaborative approach where together with the industrial, we identify the problem, we define an experiment strategy, we carry out the experiment, we carry out the data analysis, and we provide the result to the industrial partner that often is not an expert in industrial activities. We also have many EU projects with industrial impact. For example, together with the ELL and the UGA, right now we have Marie Curie co-fund action that allowed us to finance 40 PhD students project working on a project that are driven by an industrial need and are carried out using X-rays and neutrons. Similarly, we have a big project with more than 60 partners that are financed by Europe on novel technologies for autonomous discovery of advanced battery and battery chemistry. It's about 34 partners, I'm sorry. And this is on batteries. Another one is easy stress towards harmonized characterization protocols. And this is about 15 partners of measuring stress and strain in materials which are relevant for important industrial applications. And to finish, last but not least, probably the most important one, we also have a major dedication in training the next generation of scientists, engineers, and technical staff. Just to mention, during the last 6 months, we have gone through a massive recruitment campaign for beamlines. For the beamlines are the instrument that uses synchronous radiations by hiring scientists, postdoc, PhD student, and engineer. We hire something like 75, 73 people. You can see it here, mostly postdoc, but also scientists and PhD students, in order to exploit the new X-ray source. And if you are interested to learn a little bit more, you can go on our website and look for humans at the Esrf, and you have stories of many of these students coming from all over the world for carrying out their PhD and learning about synchronous radiation science. We also organize a school together with the ELL and the UGA, which is called Hercules. It's now more than 20 years old. Every year is carried out. The specificity of the school that lasts something like 6 weeks is half of the time is theory of X-rays and neutron, and the other half of the time is a hands-on experiment on our beamlines and instruments. Also, we have an undergraduate student program financed by Esrf and ELL. Is 1 month full immersion, typically in September. So we typically have something like 170 applications, so it's very competitive. And we can accept 20 students and typically coming from something like 10, 15 countries. And each one of these students is associated with a specific program that they propose when they apply for the position. You can find, again, all kinds of information of this kind on Esrf and ELL website. And finally, we also have instituted, since a few years now, a program with the Academy of Grenoble, which is called Synchrotron School, that allows pupils from high school to come for a full day immersion at the Esrf. And these pupils are, of course, coming mostly from the Grenoble area, but also from the region, from France, and from many other countries that become aware of this possibility and organize a trip of a few days in the Grenoble area to discover Esrf, giant, and having this full immersion. So Esrf is just an example of what's going on this campus. An important example, but as exciting as you can be for the work being carried out at Esrf are all the other institutes. I know very well the wonderful work that's going on with neutrons at the ELL, but also on the various initiatives on the CEA and the CNRS campus, as we have seen at the beginning. So it's really an exciting time. So what is the message? The message is you're welcome. We need you. The young people is the fuel of the future. All that we have done is for you. You have to come and grab it. On the other hand, I also want to underline that specialization, like excellence and knowledge in a specific field is so important. And then once you have that, connect with the others, because from excellence plus excellence is excellence to a power that is, for me, much larger than one, and very often two or three. So it's this synergy that is what I think the key for a future sustainable world in which more than ever humankind is able to be excellent on one side and collaborative on the other side. Thank you for your attention, and I don't know if there's any possibility to have asked questions.
Thank you very much to the Director of Esrf, Francesco Sette. I will have a few questions. We need a lot of people asking questions online, and so we'll just ask. One of the questions is, how can we apply the use of cryo-EM platform? This is from a student, a PhD student in CNRS.
Okay. If you go on our website and you look at the user part of the website, all the information are there. We accept applications at given deadlines. You have to submit a form where you express the kind of experiment that you want to carry out on the cryo-EM. Then we have a panel for peer reviewing these proposals. Is a panel of experts from all over the world that are not Esrf people, and that join together. We have all the informatic means in order to have various meetings every year, in particular for the cryo-EM that is in extremely high demand, and they decide on the proposals that are received, what are the priorities in terms of scientific quality. And then you get the beam time on the specific platform. One very important thing that we have at the Esrf is that once your proposal is accepted, Esrf pays for everything else. In other words, it will pay for your trip, it will pay for all the local expenses that you will have in Grenoble while you are carrying out the experiment at the cryo-EM or at the beam line that has been assigned to you.
Thank you very much. Okay, one more question. As a student in Grenoble, what will be the biggest impact of being part of the giant campus?
Well, I believe that the biggest impact is being able to access state-of-the-art opportunities. So nothing comes for free. So here you will find wonderful possibilities, but you also have to engage yourself in order to be an actor. What is the main purpose of Giant is to open the doors. All the doors are open. So if you are curious, if you want to do something, don't hesitate. Knock at the door where you think you should knock, and for sure, if this is the right door, you will be welcome. If it's not the right door, for sure, you will be addressed to the direction in which perhaps you can get a better opportunity for what you want to do.
Okay, we have the last question. Is there a mechanism to a new collaboration easily, since SIA is also part of Giant?
Is there a mechanism of new enabled collaborations?
A mechanism to new enable collaborations easily, since SIA
between who and who? Within Giant, or I mean,
yes.
Collaboration within Giant is something that we are working on every day. It's our real desire. There are many, many examples that we can cite where different actors got together, formally and informally, to advance on a common project. But this is not all. I also want to underline that one of the strengths of Giant is to bring people from the outside. Giant is not a closed club. On the contrary, Giant is an ecosystem that is able to live because of the energy that is inside Giant, but also the energy that is coming from outside. So Giant alone is not something that will survive if we do not have the interest and the capacity to attract resources from all over the world in order to use at best our possibilities.
Thank you very much. We have a lot of questions, but then other questions will get to answer it during the course of the program. So thank you very much to the director of ESRF, Francesco Sette.
Okay, thank you.
Thank you.
Thank you.